This is Euclid Book 11, Proposition number 6. And there is a very good reason why we have this circle. Follow my pen here. It goes all the way around like this, and all the way around like this, and all the way around like that. There's a good reason why we have that circle there. And I will explain that to you later in this proof. So hang in there. It says, if two straight lines be at right angles to the same plane, the straight lines will be parallel. Well, what's the plane? Okay, here's the plane. Follow my pen here. Straight across like this, straight down like this, straight across like this, and straight up like this. Now then, that plane is a parallelogram. It would be stretching it if you said rectangle, so let's just stick with parallelogram at the moment. Okay. For let the two straight lines AB and CD be at right angles to the plane of reference. Well, I showed you what the plane of reference are. I already showed you what the plane of reference is. So, what's line AB? AB is right here. What's line CD? That's right here, from C to D, just like that. Okay. I say that AB is parallel to CD. So what we're going to say here is that if you drew this all the way straight out here and you drew this all the way straight out here, they would be exactly parallel. They would never meet. May not seem that way according to this diagram, but yes, that is actually true, and I'll prove it. For let them meet the plane of reference at points B and D. Well, here's point B here. AB meets at point B. CD meets at point D. Okay. And let the straight line BD be joined. You say, well, how am I going to join this straight line BD if I can't even draw a line CD? Good question. So how are we going to draw all this? Well, that's where this circle comes in. I made line AB 2 inches long. And then I made line BE 3 inches long. Okay. Now at point E, I drew a circle, and this circle has a radius of 2 inches. But I didn't draw the radius right off the bat. You said, well, why didn't you do that? Because later on in the proof, you're going to find out that line AD is going to be equal in length to line BE. Now, there's only one way you can make line AD equal to BE. And that is, you draw this circle, and then you draw the length of line AD, and you make sure that this line AD is going to be 3 inches in length when it touches that circle. Then you'll know for sure. Okay? Alright. So that's how you're going to do that. Now, I suppose what you could do, because if you think about it, line AB here and line BD here are two sides of a parallelogram. You could have formulated the side of this parallelogram. You could have called it 2 inches, and then you could have figured out this other length by just drawing a parallelogram. But I just felt it was a lot easier to just draw this circle right here, draw this line here, and then from there draw this line down. It's a little more interesting way to do things, but it works. Okay? So, let's go back here. It says, for let them meet the plane for let them meet the plane of reference at points B and D, which we did. Let the straight line BD be joined. When you've got this whole diagram drawn out, you can draw a straight line from point B to point D. Okay. Let DE be drawn. Well, what's DE? Well, we just drew that. In the plane of reference at right angles to BD. Okay, so we're going to draw DE at right angles to BD. So DE is going to be at a right angle to this. I know it doesn't exactly look like it, but it is. Let's just go on here. Let DE be made equal to AB. Well, here's DE, and it's made equal to AB. And let BE, AE, and AD be joined. Okay, so now we're going to join BE, and we're going to join AE, right here, and AD. So we're joining this one, and this one. Well, we already did all that, so hang on. Now, since AB is at right angles to the plane of reference, it will also make right angles with all the straight lines which meet it and are in the plane of reference. And this is by Euclid Book 11, definition number 3. But each of the straight lines BD and BE is in the plane of reference that meets AB. Okay, so where's BD? Well, there's BD right there. And where's BE? Well, that's this one right here. And they both meet AB right here. Therefore, each of the angles ABD, well, what's the angle ABD? That's this one, and this one. And what's the angle ABE? That's this one, and this one. They are both right angles. This one's very obvious, but you'd have to look a little bit harder to see that this one also is a right angle. This to this to this is also a right angle, as is this to this to this. Okay. Let's go on here. For the same reason, each of the angles CBD, well, let's see. We have, CDB, that angle is obviously right. Okay. And CDE is also right. Okay, I see now. Because this is sticking up outside of this parallelogram, and this line is within the parallelogram, then yes, they are both right. Alright, that is right. Okay? I know it doesn't look like that, but it is. And since AB is equal to DE, since this line here is equal to this line here, and BD is the common, okay, and this line here is the common, okay. The two sides AB, BD, okay, are equal to the two sides ED and DB, and they include right angles. Therefore, the base AD is equal to the base BE, which is this one. Therefore, if this line is equal to this line, and this line is equal to itself, and they all contain right angles, then that means that this line here is equal to this line right here. There you go. And this is by Euclid Book 1, proposition number 4. And since AB is equal to DE, AB is equal to DE, okay, while AD is equal to BE, AD is equal to BE, since this is equal to this, the two sides ABBE are equal to the two sides EDDA, and AE is their common base. Therefore, the angle ABE, well, what's the angle ABE? Well, that's this one right here, and it's 90 degrees, is equal to the angle EDA. Well, what's EDA? EDA, that would be this one right there. Those two angles are equal. And that's by Euclid Book 1, proposition number 8. But the angle ABE is right. Therefore, the angle EDA is also right. This angle is a right angle because this angle is a right angle. Therefore, ED is at right angles to DA. Therefore, ED is at right angles to DA. Follow along so far? But it is also at right angles to each of the straight lines BD and DC. So ED, which is this line right here, is also at right angles to BD, which is this one right here. This one is at right angles to this one. And it's also at right angles to DC. This one is at right angles to this one. Got it. Therefore, ED is set up at right angles to three straight lines, BD, DA, and DC, at their point of meeting. Therefore, the three straight lines, BD, DA, and DC, are all in one plane. Okay, so BD, which is this one here, and DA, which is this one here, and DC, which is this one right here, for some dumb reason, they are in the same plane. And that's by Euclid Book 11, proposition number 5. But in whatever plane DB and DA are, in that plane is AB also. For every triangle is in one plane. Therefore, the straight lines AB, BD, and DC are in one plane. So, AB, BD, and DC, all three of these are also in one plane. And each of the angles ABD and BDC are right. Well, what's the angle? ABD. This one, we're going to have this one right here. This one here. And BDC, that would be this one right here. They're right angles. Therefore, AB is parallel to CD. And this is by Euclid, Book 1, proposition number 28. And that's the end of the proof. Thank heavens. Alright. I will tell you more in a future video, so I'd like for you to stay tuned.